Almost all drugs must function in solution within the body. Before an active pharmaceutical ingredient can be absorbed into the bloodstream, it has to transition from a solid dosage form into a liquid solution. This phase change is the primary structural hurdle of drug delivery. To understand this mechanism, we have to define the system. A solution is a single phase that is homogeneous down to the molecular level. It consists of a solvent, the component that determines the phase of the solution and makes up the majority proportion, and solutes, which are the molecules or ions dispersed throughout that solvent. Analyzing this system requires us to separate two distinct properties: dissolution rate and solubility. Dissolution rate is the kinetic speed of the process, how fast the drug enters the liquid. Solubility is the thermodynamic limit, the maximum amount of drug that can be dissolved when the system reaches equilibrium. In practice, high solubility is usually associated with a high dissolution rate. Because they correlate so frequently, it is easy to assume they are governed by the same rules. They are not. The widely used film coating material hydroxypropyl methylcellulose, or HPMC, proves the rule. HPMC is highly soluble in water, meaning its thermodynamic capacity is massive, yet its kinetic rate is extremely slow. A solid piece of HPMC takes many hours to hydrate and finally dissolve. To engineer a functional dosage form, a formulator has to decouple these properties, calculating the total required capacity of the drug entirely separate from the speed at which it reaches that limit. We can break the physical mechanism of dissolution for a crystalline solid down into two consecutive sequential stages, occurring at the molecular level. Stage 1 is the interfacial reaction. Solute molecules at the very edge of the crystal must overcome the cohesive forces holding them together in the solid phase. Once liberated, these molecules slip into empty cavities, often called free volume, that naturally exist between the molecules of the liquid solvent. Stage 2 is diffusion. The liberated solute molecules cannot simply stay at the interface. They have to physically migrate away from the solid surface and out into the bulk of the solution. This outward migration forces them through the boundary layer. This is a static, slow-moving film of liquid that surrounds any solid immersed in a fluid. It acts as a physical barrier. Because the liquid immediately touching the solid is fully saturated, there is a steep concentration gradient across this boundary layer, dropping steadily until it reaches the concentration of the bulk liquid. For this entire two-stage process to occur spontaneously under constant pressure, the thermodynamic energy balance, specifically the change in Gibbs free energy, must be negative. The system must move toward a lower energy state. Because the initial interfacial reaction is practically instantaneous, the slower physical crawl through this static boundary layer dictates the speed of the entire sequence. Diffusion is the rate-limiting step. Since diffusion controls the speed, we can quantify it using Fick's first law. Fick's law states that the rate a dissolved material moves is directly proportional to the difference in concentration between the two sides of the diffusion layer. This principle expanded into the Noyes-Whitney equation, the master formula for dissolution rate. To increase mass transfer, dm by dt, maximize the numerator, diffusion coefficient, K, surface area, A, and saturated solubility limit, Cs. Conversely, minimize the bulk concentration, C, and boundary layer thickness, H. If the volume of the bulk liquid is massive, the concentration of the dissolved drug, C, never has a chance to build up. When the bulk concentration remains below 10% of the absolute saturation limit, the system achieves what are called sink conditions. Under sink conditions, the subtractive C drops to 0, simplifying the math. This mimics the actual in vivo environment. When a patient takes a pill, the gastrointestinal fluids dissolve the drug, but the intestinal walls rapidly absorb it into the bloodstream, constantly sweeping the solute away and keeping the local concentration near 0. Every physical manipulation a laboratory formulator makes to speed up a drug's absorption is simply an attempt to maximize the numerator of the Noyes-Whitney equation, or minimize its denominator. This table categorizes the physical factors we can control to alter in vitro dissolution rates, mapped directly to their corresponding variables in the Noyes-Whitney equation. The most direct lever is surface area, A. If you take a fixed mass of a solid, say 1/100 micrometer cube, and reduce its size to 1,010 micrometer cubes, the total surface area exposed to the solvent increases by a factor of 10. Milling a sparingly soluble drug exponentially multiplies its surface area, but fine powders tend to cohere and clump together in liquid. If the liquid cannot penetrate the clumps, that theoretical surface area is wasted. Formulators frequently have to add wetting agents to maintain primary particle dispersion. To address the denominator of the equation, the boundary layer thickness, H, we use physical agitation. Stirring or shaking the liquid aggressively shears away the static liquid layer clinging to the solid surface, thinning the physical barrier and accelerating dissolution rate. We also need to control the bulk volume, C. In a beaker, this is easy. In a patient's stomach, volume is highly variable. This is the precise mechanical reason why heavily concentrated or poorly soluble drugs carry the instruction to take with a full glass of water. It artificially inflates the solvent volume to maintain the diffusion gradient. In a manufacturing setting, formulators have total, exact control over milling and mechanical agitation. But the moment the patient actually swallows the dose, that external control vanishes. Testing a powdered drug's dissolution rate introduces a geometric problem. As a particle dissolves, it shrinks. Large particles become smaller, meaning the total surface area A is constantly decreasing in real time, skewing the kinetic data. To evaluate a drug molecule accurately, scientists need a metric that bypasses this geometric decay. We use the intrinsic dissolution rate, or IDR. IDR measures the mass transfer strictly per unit of area, typically milligrams per square millimeter per second. By locking the area variable, IDR isolates the pure chemical properties of the drug in a specific medium. To achieve this physically, scientists use the rotating or static disk method. The raw powdered drug is compacted under heavy pressure into a solid, non-disintegrating cylinder. It is placed in a holder so that only one single, perfectly flat circular face is exposed to the solvent. As the drug dissolves, the face recedes uniformly, but its exposed surface area never changes. By isolating the rate from the geometry, IDR provides the true kinetic baseline of a molecule, giving researchers precise data before they commit to specific milling or manufacturing processes. While IDR defines how fast a drug dissolves, we still have to account for the thermodynamic limit, the point where the solution becomes perfectly saturated at equilibrium and dissolution naturally stops. This maximum capacity can be expressed through several mathematical lenses: simple weight per volume percentages, molarity, counting moles per liter, molality, tracking against solvent mass, or precise mole fractions. Predicting which solvent will yield the highest solubility for a specific drug relies on a well-worn heuristic: like dissolves like. A solute will dissolve best in a solvent that shares similar chemical properties. The mechanics behind this rule are driven by electrical affinity. Polar solute molecules have high dipole moments, exerting strong attractive forces on each other. To pull them apart, you need a polar solvent capable of exerting comparable attractive forces. A nonpolar solvent simply lacks the electrical strength to break the solute's internal bonds. Rather than relying on broad categories of polar and nonpolar, scientists use Hildebrand solubility parameters to quantify cohesive forces mathematically, assigning precise numerical values to the solvent power of a given liquid. Establishing a true solubility limit in the lab requires strict parameters. Both the solute and solvent must be absolutely pure, the solution must reach perfect equilibrium with excess undissolved solid present, and the temperature must be rigorously controlled. Solubility cannot be brute forced. It is an unyielding thermodynamic equilibrium, strictly dictated by the electrical affinities operating between individual molecules. While the equilibrium is strict, formulators have several methods to manipulate the capacity of the system. The first is temperature. For most drugs, dissolution is an endothermic process. It absorbs heat. Supplying heat directly increases the drug's solubility limit. Looking at the solubility curves for various substances, notice the anomaly with sodium sulfate. Solubility climbs as heat is applied until exactly 32.5 degrees Celsius. The crystal physically converts. The process becomes exothermic, and its solubility capacity sharply drops. If heat is not an option, formulators can alter the solvent itself. By adding water-miscible cosolvents like ethanol or propylene glycol, they can drastically increase the capacity of the liquid. The drug metronidazole, for example, relies on co-solvents to achieve high concentrations necessary for intravenous antibiotics. Formulators can also manipulate the physical geometry of the drug crystal itself by forcing it into a slightly irregular, metastable lattice. This property, called polymorphism, means the constituent molecules are aligned differently within the crystalline structure. This metastable form carries a higher internal free energy, requiring less work from the solvent, resulting in a higher total solubility. Finally, chemists can alter the molecular structure of the solute. Converting a weak acid into a sodium salt increases ionic dissociation in water, spiking its solubility. Conversely, modifying a drug via esterification can intentionally drive its solubility down. This is frequently done to mask bitter tastes in pediatric suspensions or protect against premature degradation. Reliable drug delivery depends on a dual-track strategy, engineering the physical geometry to optimize the kinetic speed of dissolution, while simultaneously aligning chemical affinities to maximize thermodynamic capacity.